for each of the properties, and I've been able to do that. I've also forwarded the calculations to your course rep, and I'm sure he will forward it to all of you to go
Yes, sir,
through
he shared
it.
it with us.
Thank you very much. So we're not going to stay here any longer. We'll move forward. We'll go through the calculations. Anywhere you are not satisfied or you have issues, you can see maybe on Friday or when you come for your revision. So we'll continue. The next thing we're going to do is continuation of the physicochemical parameters, the ecological importance of physicochemical parameters. I've looked at a number of them, and we're continuing. We're going to look at the next one is talking about molecular attributes, which has to do with electronic properties. So not wasting time here. But what we have before us here is that if you can calculate certain electronic properties of molecules, it is useful, or it becomes very useful for estimation of how reactive or the reactivity of that chemical with biological targets. So knowing the calculated electronic properties of molecules can be a useful part of a first-tier estimation of a chemical's reactivity with a biological target. And for some endpoints, electronic properties have been shown to be helpful in identifying chemicals of high toxicity. So there are certain calculations or numbers that you are able to get from a particular molecule. You can predict how toxic that substance can be. Like in the case of partition coefficient, for instance, if I give you the various partition coefficients of certain chemicals, you'll be able to predict how that material can affect maybe a biological substance, or how it can, how fast it can be transported, or how it can behave in the environment. Because yesterday we agreed that a material or substance or a chemical that has a high value of partition coefficient is likely to have attachment with the organic, components of the environment, kind of. And those with small amount of partition coefficient would be more, mobile, kind of, in the environment. And the same thing applies to what we're talking about here. So if we're able to get the numbers, you can predict that this material or this substance can be toxic, this substance can behave in this way, or it can affect a particular media in a particular way. So these properties can be readily estimated with what is called quantum mechanic calculation. This is chemistry. So I'm not going to confuse you here or bore you with some of these things, because many of you are started complaining that, oh, this is chemistry. So I'm not going to talk more than this. So when you have these numbers, you'll be able to predict, you know. So like I said, these properties can, the electronic properties, that is what I mean, can be readily estimated with quantum mechanic calculations when the chemical structure is known. So if you are able to know the structure of a chemical, it is possible for you to do some predictions through, this quantum mechanics. So I'm going to stop at that. Just try to show the picture of what we're talking about here, and I won't talk about this because it will it will make you get a bit agitated. So we'll leave it at that. So this table is giving a kind of an overview. It's giving us an overview of physicochemical properties and rationale for use in hazard assessment. So when someone is talking about flammability, for instance, which is a physical property, you know that it is associated with flammability hazard. Flammability, that is how a chemical can, become flammable, so to speak. And then you have corrosivity. Corrosivity, that has to do with a material or a substance that is corrosive, like acids. Okay, they have ability to destroy materials through chemical reactions. If you add an acid to a metal, it will corrode that metal. Okay, so that property is known as corrosivity, and it's a physical property. Okay, then you have oxidizing ability. There are some chemicals that have oxidizing ability. All right, when we say a material or a substance or a chemical has oxidizing ability, it means it is associated with the ability to give off oxidizing substances or oxidized combustibles materials, increasing fire or explosion hazards. Okay, oxidation has to do with, maybe burning in the presence of oxygen. So where you have a substance that can easily, cause fire outbreak by use of oxygen. Okay, something like that. And then you have the melting point, the boiling point, the impact environmental fate. So a substance that has a low melting point, you should begin to, that will tell you whether that if it has high melting point, you know that it will take time before it will melt, and then maybe get into the various environmental compartments and then affect the environment and so on and so forth. The same thing with boiling point and vapor. You have a material that vaporizes very easily and is toxic. You know that it will be very harmful compared to the one that takes time before it vaporizes or it boils and so on. So that's the kind of relationship we are having here. Then you have solvation. That one has to do with solubility. Okay, determines ionization state in the environment as well as biological compartment ionization state in different parts, such as water solubility, partition coefficient, and so on. So this is a kind of summary on how each of these property, can be related to the kind of effect it could have on the environment, and so on and so forth. So it continues. So any challenge, any question? I hope you're following me at the moment.
Yes, sir.
Yes, sir. Yeah, we are following you, sir.
Right. So I want us to look at this aspect now, using physical-chemical properties to assess chemicals, physical hazards, environmental fate, human and ecological toxicity endpoints. I always tell you not to mind so much about the big headings. Sometimes they are repetitious, so you don't need to be scared by the big heading. Just understand the meaning or the importance of what we are trying to talk about. So first is physical-chemical properties and physical hazards. We are told that the first step in using physical-chemical properties is to determine the likely physical hazards. Determine the likely physical hazards. So properties like flammability, we have looked at that, know what that means. Gases under pressure. A gas that is under pressure, is dangerous. Oxidizing liquids, corrosivity may cause physical hazards. That we all know. The gas that is under pressure can explode and cause, serious hazard. But there are rare cases where these properties might be desired in the final product, like fireworks, lighter fluids, and so on and so forth. Now, physical-chemical properties and environmental fate. I mentioned earlier, and I think I have explained what we mean by environmental fate. We're talking about environmental fate of a chemical. You are trying to look at. It has to do with how long does that material stay in the environment before maybe it degrades, and so on and so forth. Does it degrade very fast? Does it stay in the environment for a long time, or does it stay for a short time? And the number of time or the amount of time that a chemical will stay in the environment is also a product of the kind of effect that it may have on the environment. So if you have a chemical that stays in the environment for a very long time, you know that it will cause, a gradual effect over a long time, and it is quite dangerous. There are some that stay just for a very short time, and then they get converted. So when you're talking about environmental fate, it has to do with how long, the chemical would stay. Do they persist for a long time, and so on and so forth. So the second step in using physicochemical property is to determine the environmental compartments into which the chemicals will partition. So the chemical's physical state, which can be predicted on the basis of melting point, boiling point, and vapor pressure, can indicate which environmental compartments, all right? That is air, water, sediment, biota, soil, into which the chemical will partition. So if you have a chemical that is gaseous in nature, then you should know that the environment or the compartment in which that chemical will find, will be inclined to, it will be air. Okay? Something like that. So into which it will partition. So Highly volatile chemicals, for example, escape from soil or water and primarily be present in the air. I think that's what I've said. So chemicals that are highly volatile, they will escape from the soil, escape from where? From water, and then be found in the air. Okay? Now, conversely, chemicals with high propensity to sob onto organic carbon. You know that organic carbon, you can find it in the soil, right? So substances that have that affinity of absorbing or adsorbing onto organic carbon or move into liquid phases are likely to retain in the soil or sediments or move into the biota, respectively, because they are more inclined to organic materials. They are more inclined to organic matter or organic carbon. So where you can find where it can attach itself easily, it will be in the sediments where you could have organic materials, or it could be in soil, or it could be in the biota, right? So that is how we can, you know, see how this could affect the environment in which they get attached to. And again, aqueous solubility will provide information about whether a chemical will dissolve in water, right? Aqueous solubility, that has to do with liquid, okay? We provide information about whether a chemical will dissolve in water, right? The starting point for understanding is fate and transport into the water column or sediment. So if you have a chemical that is in liquid form, for instance, then you should know that it will or has the ability to dissolve in water. You know that it can leach into the groundwater, all right? Something like that. So that is how these properties can be used to predict fate or to predict where you can find them. So what we're talking about is where you can, find them based on the properties in which they exhibit. So it's almost the same thing if you go down the slides. Any question? Any question? Any comment at this point? Does anybody has a question to ask? Because we're moving a bit faster now because of time. Okay. Wange's hand is up. Yes, Wange, can you speak?
Good morning, sir.
Good morning.
Thank you for the wonderful lectures. I have a little concern.
Okay.
As in the difference between the half-life of a chemical and the environmental fate. So I don't know if they are the same or they are different in definition or meaning. Thank you.
Right. Half-life and environmental fate. That is half-life of a chemical and environmental fate of a chemical. I think I'll say that half-life is simply the time. Half-life has to do with the time, which is also fate or kind of fate. But half-life of a chemical, it is the time that is taken for the original concentration of that substance to reduce to half of it. So if you have maybe 20 moles, if you have, say, 20 moles, that person should stop disturbing us now. If you have, say, 20 moles per day cube of, let's say, DDT, and 20 moles, that is the original concentration. You can take that one as the original concentration or the initial concentration. So you have 20, and maybe after 10 hours, maybe it is introduced into a medium, or it is introduced into the environment. And after maybe 10 hours, you measured it, and what you got was 10 moles per dm cube left. That is half of 20. So in this case, you can now say that the half-life of DDT is 10 what? 10 hours. Because it is after 10 hours that it was able to reduce to half of that number. So if it takes it so that can be referred to as half-life of it. And you can see where the fate comes in now. There are some that have shorter half-life. For instance, maybe you have a particular chemical that disintegrates maybe within 10 seconds or within 5 minutes, and so on and so forth. So from the half-life, you'll be able to tell about the fate of a particular chemical, whether it persists for a long time or it doesn't stay for a long time in the environment, and then it gets, it disappears or something like that. So the half-life has a relationship with fate, because from the half-life, you'll be able to tell whether the substance or the chemical can stay in the environment for a particular time before being discarded. Do you understand?
Yes, sir.
Is that explanation okay for you?
It's taken, sir.
All right. So we look at these properties in relation to persistence, bioaccumulation, and biotransformation. These are very familiar terms, at least for those of you who are in the environmental sciences. So first, I'd like you to know that organisms take up and eliminate chemicals at different rates. And when the metabolic detoxification or excretion or removal, when the removal of these chemicals or the excretion of these chemicals by organisms appear to be slower than uptake, the chemical or the chemicals accumulate in the organism. All right? If it takes a long time before a particular organism gets rid of a particular chemical, the chemical tends to accumulate in the system of that organism. Unlike when, as it enters the system, it is leaving the system almost immediately. At that point, there is no likelihood of buildup. So what we're talking about here is that organisms take up and then build up these chemicals in their system. It is that process of, building up of these chemicals in the organism's system that we refer to as accumulation or bioaccumulation. And like I said, the chemicals tend to accumulate in the organism, resulting in prolonged tissue delivery. It takes a lot of time before the chemical is delivered from the tissues. If not, they will get accumulated into the system, into the tissues of these organisms. So some of these chemicals increase in concentration at each level of the food chain. All right, they increase in concentration at each level of the food chain. These chemicals are said to be biomagnified. Biomagnified. That is what we refer to as biomagnification. Okay? Now, assume what I mean by biomagnify here. Assume that you went to the river, the smaller fishes in the river took up maybe a particular chemical, and the bigger fish came and fed on that chemical, all right? I mean, fed on that small fish, and maybe a much, much bigger fish is feeding on that one, up to the point that human beings have also, maybe gone to feed on that bigger fish that is feeding on the smaller fish. In that case, what you are going to experience is going to be biomagnification. That's why some chemicals increase the concentration at each level of the food chain. Each level of the food chain. These chemicals are said to what? To biomagnify. Because of the potential of some chemicals to biomagnify and persist in the food web, bioaccumulating substances require special consideration because they may pose a greater hazard than right. Are we together now? Hello? Hello,
We are
guys.
yes, sir. We are together, sir. Yes, Prof.
Okay. Yeah, network has been a bit bad, but at my end, I think my network is fine. So that is that. So large chemical structural databases combined with recent developments in quantitative structure property relationships have greatly expanded the potential for rapid assessment of chemicals. That is just trying to, tell you how recent developments have been able to help in assessment of this chemical. So thus far, efforts using these models have proven successful in identifying potentially persistent, bioaccumulative, and toxic chemicals. Persistent, bioaccumulative, and toxic. That one is abbreviated by PBT. Now, so what do you mean by persistence? Mind you, we are looking at persistence, bioaccumulation, and biotransformation. Persistence of a substance. I've been mentioning this thing since we started this lecture. It has to do with the length of time. Okay, a chemical, a substance can reside in a particular environment before it can be moved away from that particular environment to another one. Okay, or it can be transformed either chemically or biologically. So that is what we mean by persistence. It has to do with the time, okay, a chemical remains or resides or stays in a particular environment before it is physically transported to another compartment and or is chemically or biologically what? Transformed. That is what we mean by persistence. So you can see that chemicals that persist in the environment have their concentrations increased. And for that reason, they have greater impact in the environment where they find themselves. And such chemicals are likely to do what? To bioaccumulate. Okay? For some classes of materials, we are told that it is possible to obtain useful predictive information about potential persistence from physicochemical data. So when you have these numbers, it is possible for you to predict, like I said, in the case of partition coefficient, and it is mentioned here too. So if you are able to know the structure of a particular chemical, you are able to know the partition coefficient of that particular structure, you can predict how long it can stay in the environment before it will be transported or transformed either chemically or biologically, and so on and so forth. So the persistence of a chemical in the environment is often measured or estimated in terms of what is called its biodegradation. Biodegradation. So what is biodegradation? It has to do with the what? The breakdown, okay? Breakdown, okay, of a particular chemical through a number of processes. It could be a chemical process, it could be a biological process, it could be a physical process, right? So the persistence of a chemical in the environment is often measured or estimated in terms of its biodegradation. Biodegradation. Although here it is specific, biodegradation has to do with the breakdown of that chemical through the activity of microorganisms. That is what we mean by biodegradation. Okay? So there are numerous modes of degradation that depend on environmental conditions too, types of microbes that are present, okay, and the structure of the chemical. So if you have a chemical that has a complex structure, very complex, you know that it will take time before it will be biodegraded or broken down, all right? Than when you have a structure, a chemical that has a very simple structure, all right? It will take time for it to be what? To be degraded, okay? So that is how you can measure. Read what we wrote here, that there are numerous modes of degradation that depend on the environmental conditions, types of microbes present, and the structure of the chemical. So degradation is typically quantified based on the extent of removal of dissolved organic compounds within an aqueous medium of a chemical and is expressed as a percentage of degradation in a given time. Okay? So some of these things are language that you can read and understand. Then we have chemical degradation, like I mentioned, a subset of biodegradation. This one has to do with hydrolysis, photochemical transformations, and the actions of microbial species. You know, so this is just telling you how these chemicals can be broken down and how they can be transported, how long they can stay. It depends on the number of factors, like I've mentioned. So you can read a number of them up. And the next one I follow is structural attributes that enhance biodegradation. I've told you about the structure. I said you have a chemical that has a complex structure, okay, or has some attachment or moieties that are difficult to break. It takes time. It takes time. So you can begin to measure them, you know, in that manner. So structural attributes that enhance biodegradation. So these are the attributes that when a chemical has, it can be easily biodegraded, like minimal number of halogens, especially fluorine and chlorine. Okay? If you have a chemical that has a minimal number of fluorine and chlorine, then it is likely that it can be easily what? Degraded. You have the one that has minimal chemical branches. I think I mentioned this yesterday. You know, how much of it is branched? You have so many branches, carbon atoms, you know, carbon bonds, plenty of them. It will take time before it will be biodegraded or degraded, okay, for you to be able to measure persistence. So you can see that a material that is difficult to be biodegraded, it will persist in the environment much more than the one that can be easily degraded, okay? So the one that has minimal number of tertiary, amine, and so on and so forth, presence of ester, presence of oxygen atoms, okay, presence of short linear alkyl chains, less than 4 carbons, you know, these ones can be easily degraded. All right? Hello? Any question? Are you following?
We are following, sir.
Yeah, so another thing I want to say is that most of these things are a kind of repetitions, and the repetitions are not just for repeating them for repeating sake. It's for you to understand, you know, the meaning, or understand, you know, have a better understanding of the topic, you know. So you can see that most of the things that we are saying will just be repeating. It's for clarity. It's not for anything. It might be saying a different way, but the same meaning. So we are still on physicochemical properties, and in this case, prediction of inorganic chemicals bioavailability. All right? So we say that characterizing the lifetime of metals, for instance, as an inorganic, you know, or as inorganic materials. Metals are inorganic substances. So characterizing the lifetime of metals in the environment Lifetime, that is faith. You know that faith, lifetime has to do with faith, has to do with persistence. Okay, how long will it persist in the environment? So these things are used interchangeably. So characterizing the lifetime of metals in the environment is difficult. Why is it difficult? It is difficult because of the interactions are highly dependent on the list where they are. So leaching and aging are related to conditions within the soils and sediments. So predicting environmental hazard based solely on standard aquatic tests using dissolvable salts is not adequate. So you cannot just use a particular method in doing that because the chemical is interacting in different ways. Therefore, the field of ecotoxicology is becoming increasingly reliant on sediment and soil toxicity test protocols that include leaching and aging steps, okay, or the application of bioavailability models, okay. You can use models, so on and so forth, to adjust data acquired under laboratory conditions to realistic conditions in soil, sediments, and water. So these are a number of stories that you can go through and appreciate better. We're still talking about bioaccumulation here. Bioaccumulation is presented in the most alternative assessment schemes. It's another way of determining, the behavior of these chemicals in the environment. So if you are able to do what is called bioconcentration factor, that will tell you, give an idea of the bioaccumulation potential of a particular chemical, right? And in this case, what do you mean by bioconcentration factor? It has to do with the ratio of the concentration of the chemical in an aquatic organism. Okay, for instance, usually fish, to the amount of chemical in the water under conditions of equilibrium. So if you want to know bioaccumulation factor, for instance, of tilapia fish in River Benue, the fish, you can find tilapia in River Benue. So what you need to do is to determine the amount of that chemical in the fish. So whatever value you get, you note it. You will then determine the amount of that chemical again in the water. So when you divide what you have in the fish over what you have in the water, you multiply by 100. That gives you bioconcentration factor. It will tell you the extent, the degree to which the chemical, is available in the sample, so to speak. In this case, the fish. So we are also told that there is an alternative approach to measure bioaccumulation factor. Alternative approach is to measure bioaccumulation factor. And bioaccumulation factor is a ratio of the amount of chemical in the fish to the amount in both food and water, okay, expressed on a molar basis and frequently normalized to lipid content. So these are some of the ways that you can measure. You may not have direct experience with this in the course of your lecture, of your study, but it is good that you have an idea of some of these things. Very, very important. Okay. Hello.
We are with you, sir.
Right. Now, there are some terms that we need to know, like bioavailability, bioaccessibility, and toxicity. A chemical that is highly bioavailable has higher potential to cause harm than the one that is less bioavailable. And the one that is highly bioaccessible, I'm going to explain, is likely to have less, potential to cause harm. So bioavailability is a measure of the amount of a chemical and the rate at which it crosses a barrier of the external environment and enters an organism's circulation. That circulation is blood. Oh. That's what it means. It's blood. It's blood. I will explain. From there, the chemical can reach tissues in living systems and interact with cellular macromolecules, adapted from the study of metals in the environment and chemical bioaccessibility. Well, now, let me just explain. Sometimes all these notes, you get confused sometimes about them. But when you get the meaning of what it is, every other thing becomes simple. Now, let me explain what is bioavailability and bioaccessibility, and then you read the rest under it. Now, when you are talking about bioavailability with respect to, let me say, an organism, it is the amount of that chemical that is able to enter the blood system. Are you hearing me? The amount of chemical that is able to enter the blood system. Now, when you are talking about bioaccessibility, this one tells you how much of that chemical is available in a particular compartment, maybe in the stomach region, something like that. But mind you, that has not entered the human or the bloodstream. Bioaccessibility, that is what you can assess. But when you're talking about bioavailability, is how much you can take from what is assessed, what you have assessed. For instance, you have 10 million, or you went somewhere and you saw 10 million. That is bioaccessibility. Let's use that analogy. You saw 10 million. Now, and I say you should take from that 10 million. And because maybe you have a small bag, you won't be able to take that 10 million. Maybe you were able to take 1 million out of the 10 million. In this case, bioaccessibility is the 10 million that is available for you or that is accessible to you, but what you were able to take from what was accessible was only 1 million. That is bioavailability. So the amount of chemical that will enter the blood system from the larger concentration of that chemical is what is referred to as bioavailability. But bioaccessibility, it is what is accessible, what is available for the system to absorb into the blood system. I don't know whether that analogy has made any sense. Hello? 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 Hello?
We are with you, sir. We are with you, sir.
Did you understand that analogy?
Yes, sir.
That's okay. So, in a summary form, like I said, bioaccessibility of a chemical is how much of that chemical that is accessible, or is available for absorption into the blood system. The bioavailability is the amount that enters the blood system. So if you don't understand at individual level, you can contact me, no problem. Since you say you are all right, we can move forward. So these are just, like I said, repeated kind of information. You know, we have aquatic bioavailability. Okay, that one has to do with the amount of these chemicals in aquatic species. Aquatic, that is river. River. So the organisms that are residing in the river. So in aquatic species, it is known that bioavailability is positively correlated with log P of the chemical. Log P there is still partition coefficient. Do you understand? It's just that when you change those values to log, it becomes log P. It's just for convenience. There's nothing big about that. So if you have different partition coefficient values and you decide to convert them to logarithm, that's what that means. It's the same thing. So in aquatic species, it is known that bioavailability is positively correlated with log P of the chemical, that is partition coefficient of the word chemical, in this case in log form. Although the linearity of this relationship is not clearly defined, it is also known that aqueous solubility, molecular size, and ionization states also influence bioavailability. So it is not just partition coefficient that influence bioavailability. There are other factors too, like molecular size, ionization, and aqueous solubility. I think that is quite clear. And pH is also important, because very, very important, because especially when it comes to distribution coefficient. Distribution coefficient has to do with the individual species. It takes into account the individual species of a particular chemical, because there's a chemical that might exist in ionic form, there's a chemical that may exist in a neutral form. So what distribution coefficient does is to account for all those ones. And in fact, when you're doing distribution coefficient, pH plays a critical role. So the log P at environmental or biological pH, that is log D, that D means distribution coefficient, has been proposed as a measure that correlates with partition and ionization. So you may have these chemicals in form of ions. You may ionize kind of, and then you have those that may not be in the ionic form, and so on and so forth, right? So the biotic legal model, it is a method of assessing metabioavailability. availability, that you don't need to bother about some of these big words. So we say the biotic ligand model is used when considering metal bioavailability to aquatic species, as it releases competitive metal binding to ecotoxicological effect. These are just big words, okay? Big words. You don't need to bother so much about it. The most important thing is for you to know that bioavailability can be measured, okay, using this kind of model, for instance, and that there are some factors that affect bioavailability, and not just partition coefficient, so on and so forth. Then we have aquatic toxicity. That is also something that is quite simple. An example of how physical quantum can be directly used to estimate ecotoxicological endpoint is acute aquatic toxicity. So we can use toxicity, or we can use what is called acute aquatic toxicity to estimate ecotoxicological endpoint, or estimate how these chemicals can affect aquatic organisms. Any question? Any question? Hello? Okay, Adoga. Right.
If you have a question, raise your hand up.
Yes, there is a question from Adoga. Adoga, can you speak?
Good morning, sir. Good morning, class.
Adoga.
Good morning, sir. Thank
Yes.
you, sir. Thank you.
Go ahead.
Thank you. Thank you for the delivery, sir.
Thank you. You're welcome.
So I think our this course, environmental sustainability, revolve around this your course, this chemical effect, ecological effect of chemicals on the environment. If I'm not mistaken.
Yes.
Because we did environmental monitoring because of this particular issue, chemical effects, to track pollutants. We did EIA, environmental and social impact assessment, particularly because of this course again. We did practical issue in environmental standard because of this case. So I think it would be right if I say this is the heart of this our course. And straight to my question, sir.
Yes.
Now, is it possible for us to have the idea of the permissible level of those chemical substances? I mean, the regulatory standards, which level a particular chemical, the volume that is acceptable to the environment. Suppose in real life context, as an environmental expert, if I have the task of tracking maybe chemical emissions for oil companies, and knowing fully well that there will be VOC from there, volatile organic compounds. What are the standards, the threshold that those pollutants should not exceed, so that in my measurement, I will now be able to ascertain that your company is performing within the acceptable threshold, or is going above the permissible level?
Yes.
Thank you, sir.
Thank you for that question. Yes, it is possible. It is something that even yourself can do, not necessarily me providing such information for you. Okay? You only need to go to NESRA website or some of these regulatory bodies like World Health Organization. NESRA is Nigerian thing. Okay? Ministry of Environment. You have a number of these regulatory bodies that have the various permissible or guideline values for these chemicals. So it is something that can be done, and it is quite simple to do it. I don't necessarily need to provide them for you, but I will advise you to go to NESRA website. You'll get a lot of information about guideline levels or permissible levels of some of these chemicals that we're even discussing here. But if that will be difficult for you, not something that it is so difficult to do. Just to check NESRA, you can browse. The big phones that you have can provide every answer to your question, every answer to any question that you have. The only thing you need to do is to go online information. Like I told you, for everything in the slides, it may be more than 500 pages, and students get discouraged when you have plenty notes. That's why I try as much as possible to bring out the main point from each topic, so that when you are reading, you will know that you are not lost at any point in time at all. So yes, you can get them, okay? Hello, Adoga? Hello?
Yes, I've heard you, sir. Thank you, sir. Yes,
right.
Noted, sir. Thank you.
Okay. So now you can see we have a table here that is mentioning a particular physical property and then changes. A particular here, the physical property here, for instance, here you have molecular size and weight. So the molecular size of the chemical would also determine the kind of change, all right? Or how much of that chemical will be available in the environment, and so on and so forth, and the weight. Now look at the change. Generally, as molecular weight increases, you hear that aquatic bioavailability and toxicity decrease. So the heavier the chemical is, the less it may be available or cause harm to the environment. All right? At molecular weight greater than 1,000 atomic mass unit, bioavailability is completely what? Negligible. So that is the kind of information you're going to get. For each physical property, what kind of change will you observe, okay, for that particular chemical? But caution must be taken, however, to consider possible breakdown products that may have molecular weight less than this and exact toxicity. So, in as much trespass. Oh, who's that now?
You. It is weekend, a beautiful weekend, a lovely weekend. And how do you see yourself in the...
Who's this? Hello? Hello?
We can hear you, sir.
Right. So I was just trying to tell you how these physicochemical properties, can affect bioavailability or toxicity, as the case may be, in aquatic environment. It's not just aquatic environment. What we're talking about here, can extrapolate it to even soil, sediment, and so on and so forth. It's not necessarily aquatic environment because it's the same kind of idea. Okay. So you have the same thing. Yeah. So we can also look at these properties with respect to mammals and humans. Okay. Hello, can you hear me now?
We are with you, sir.
And just like we have tried to estimate so to speak, toxicity in the aquatic environment, it's also possible to do so based on available physicochemical data to predict, to estimate toxicity of these chemicals in humans and even other animals. And here, the key thing that we look at is the processes that are involved. Processes. And this includes absorption, distribution, metabolism, and excretion. So the focus here is on the influence of physiochemical properties on the rate of absorption, for instance, of a chemical into the bloodstream. How is it distributed to the organs and the tissues? And at what rate is it eliminated or removed from the system? That is a chemical removed from the system. So there are a number of factors or properties that have been shown to impact the chemical toxicokinetics, that is in humans. We have molecular size and shape, lipophilicity and hydrophobicity. You have ionization potential, you have hydrogen bonding, and so on and so forth. So these are some of the properties that have been shown to impact the study of toxicity in humans. This so you have exposure route, the route through which maybe human beings can be exposed to the chemicals. That's combination of property limits associated with increased bioavailability through the four main routes of exposure in mammals. Then the first one is it's a ocular. Ocular. What do you mean by ocular? I was thinking somebody will ask, what do you mean by ocular? Hello? 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 Exposure route, ocular. Is it not eyes? Has to do with eyes. Oh, okay. Are you hearing me?
With you, sir.
So I said the first exposure route of these chemicals into humans is through what? Ocular. And I was asking, what do you mean by ocular? And I said it has to do, okay, it is eyes. Okay, related to eyes. Okay, I've seen some of your answers. That's okay. That's great. So physicochemical property here, water solubility. You know that if it is soluble and it gets into the water and it gets into your eyes, you know what that can mean. So the property limit is variable. Okay. Conjunctiva, epithelium, blah, blah, blah. These are the effects that it may have. And the level. The aura has to do with mouth, is it also? Through mouth, can be through respiratory lungs, okay? I mean through lungs. It can even be through the skin. Can even be through the skin. So this is oral, this is inhalation, and that is derma. Okay? So just showing the routes through which we can get into the listing. So, freight and transport of chemicals in the environment. This is not new to you. Modern societies need to understand their environment in order to assess the behavior and effects of chemicals that they use. Okay? So when we talk about chemical transport, what do we mean? It has to do with the processes that move chemicals through the environment, okay? It has to do with movement of chemicals from one maybe environmental compartment to another. And then we have been talking about fate. It has to do with the eventual disposition, you know, either destruction or long storage of chemicals. Here it's talking about time, how much it can reside before it can be removed, or how much it can be stored in the environment, and so on. And we are told that surface waters, soil and groundwater, for instance, and atmosphere have their distinct characteristics, but there are also many similarities in them, okay, where chemical exchanges occur among them. They are distinct, but you can see that if a chemical is found in the soil, it does not mean that it will remain in the soil. It may be found in the soil for a particular time and then move to, if it's one that volatilizes, okay, it can evaporate into the air medium. Or if it's a type that can move, okay, through runoff, it can be transported or can be moved from the soil medium to where? To the water medium. So in as much as these compartments have distinctive characteristics, there are also many similarities among them that ensures chemical exchanges, okay, or that ensures that chemical exchanges, take place in the various media. So knowledge of the principles underpinning the environmental fate and transport of these chemicals allow us to make informed decisions, that will protect both the human health and environment itself and solve problems ranging from local to global scales while allowing us to enjoy the benefits of modern technology. So I'm not sure, I don't know whether you can see this very well, but it's just trying to show how, these chemicals can be transported or can be moved, okay, in the environment, all right? Like you have those in the water there, they can be evaporated, they can be transformed, okay, through the action of maybe microorganisms. They can dissolve. You have dissolution there, can dissolve, they can biodegrade. As they biodegrade into maybe smaller units, they can be carried from a particular point to another, so on and so forth. They can become sedimented, okay? Sedimentation is there, okay? There are a number of these processes. Dissolution is there. They can aggregate. They can aggregate. And when they aggregate, they become deposited, maybe on the soil or in the water body, and so on and so forth. They have transport to the shore, transformed compounds. They can evaporate too, from the land. They can evaporate, or from the river or water, they can evaporate. So this is just showing you how these chemicals get, transported and then moved, so to speak, in the environment generally. Have a number of them, okay? Evaporation is taking place, evaporation, volatilization, okay? Seepage, they can seep into the soil, right? There could be precipitation, the gases may dissolve, right? And so on and so forth. Just showing the same kind of thing. Right. So we also need to be conversant with concentration. Concentration is another important aspect of this course that you need to know. And concentration has different units, and you have different ways of describing concentration, okay? So these chemicals, they exist in quantities. That is what I want you to know. They exist in different amounts. So it's a different quantities that you are calling concentration. Maybe if you take, for instance, let's say mercury, okay? You can measure mercury in milligrams per liter if it is water. You can measure mercury in milligrams per kilogram if it is a solid material. I mean, a solid media that you are looking for it in. If it is air, to be cubic, and so on and so forth. So the single most important parameter in environmental fate and transport studies is chemical concentration. And like I said, it is defined as a measure of the amount of that chemical in a specific volume or mass of air, water, soil, or other materials. It could be sediment, it could be food. So how much of this chemical is found in food? You should be able to tell us, okay, you have so amount in water, so amount in food, so amount in soil, something like that. So concentration is a measure of how much of the chemical, okay, is present in a particular media, right? So another thing is unit. Concentration has different units, just like I said. If you are determining a particular material in water, that will have to be in liter, whatever amount in liter. For instance, if you look at here, the second paragraph here is mentioning a number of units there. You say the choice of unit for concentration depends in part on the medium and in part on the process that is being measured or described. So in water, a common expression of concentration is mass of the chemical per unit volume of water. All right? So in this case, it's what? Milligram per liter. That is, we're finding a solid in water. So that is milligram per liter. If you are looking for a solid in soil, for instance, it will be milligram per kilogram or gram per gram or microgram per gram, okay? Because they are all solid. So then you have other unit of concentration in water like molarity, okay? Then you have normality, you have a number of them. So you read them up, please. You read them up. You have a number of these units. I will not waste much time to go through. I want us to skip this mass balance. We will do it tomorrow. So we'll leave mass balance today, do it tomorrow so that we'll explain it better. So let's go to physical transport of chemicals. Physical transport of chemicals. Hello, are you there with me? It's been quiet.
Yes, sir.
Right.
Profoundly with you, sir.
That's okay. So you have these notes, right? I think I've sent these notes to you. You have them. So you'll be reading them too.
Yes, sir. I've also shared it with the class, sir.
That's fine. And the calculations too.
Very well, sir, this morning.
Okay, I will do that shortly. Someone is asking a question. But some of these things you just need to browse them. You can ask AI, will tell you, this is postgraduate, so don't expect that I will give you everything. It is also expected that you find a way of getting some information that you're not very clear about. Okay? Right. So most physical transport of chemicals in the environment occurs in the fluids. Okay, it's just telling you, how these chemicals are transported. And it can happen through water, can happen through air. These are the basic or primary route through which these chemicals are transported in the environment. You have bulk movement of fluid from one location to another. When that happens, we refer to that as advection. Okay. Then you have convection, right? It has to do with wind. Okay. Movement through wind and flowing streams. All right. These things are quite self-explanatory. You have dispersion, diffusive, and so on. Diffusion, movement from high concentration to low concentration, and so on and so forth. Okay, so you read that up to this. This one too is self-explanatory. Look at the examples. Modification by that molecular. Okay, this ones I will sit down and get them out properly. Then we'll do it. We'll do it together. In fact, most of these ones that involve calculation, I want to crave your indulgence that we do it during revision. You go through it, and where you have issues, you will look at them during revision. Because we start to do those calculations now. They start taking us unnecessary time since you are not physically here present to answer some of these questions. So we will do those, try to see how you can solve those problems yourself. And then we'll now see how we can use that 1 week. That 1 week of revision, it will be enough for us to cover, to attend to concerns and challenges because of time. So let's look at toxicants. Toxicants. What do you mean by toxicants? What do you understand by toxicants? It's a question. So under these toxicants, we're going to look at formation. Mind you, toxicants are also chemicals. We are talking about chemicals here. So toxicants are chemicals, but these are some terminologies that you need to know and that they are used in toxicology and so on. So it is also, they are chemicals, but what do you mean by toxicants? Can someone tell us what toxicants are? Oh, Dugeri.
Yeah, good morning, Prof. Yes, sir. Good morning, sir. Good morning, my mate. I want to react to the question you just asked about toxicants. They are just agents that are capable of causing disease in the environment.
They are what?
They are chemical agents that are capable of causing disease in our environment.
Okay, they are chemical agents that are capable of causing diseases in the environment. Okay. Any other? Any other? Hello? Any other? Hello?
Yes, sir. Some are dropping in the chat box.
Okay.
I would like to read a few.
No, don't worry. Let me get this ones who their hands are up. Because, yes, Paul over. Paul.
Yes, sir. Good morning, sir. The prof, good morning, sir. Thank you so much for the very wonderful lecture. In fact, we are really grateful for the lecture. So, toxicants can actually be toxic substance, or even that's artificial or natural substance that can cause harm to the environment or living organisms. And
you have added something there, is it also?
Oh, okay.
Added, you said natural or what?
Natural or artificial. That's toxic substances, whether natural or artificial ones.
I agree with you. The other person says chemical agents that are capable of causing diseases in the what? In the environment. So you have now added another idea there. Say natural or what? Or synthetic.
Or artificial. Yeah, synthetic. Yes,
that's
sir.
Right.
Thank you, sir.
Let's hear from Ben. Uwa, you can put your hand down.
Hello, sir.
Yes, Ebenyi Michael. Can you go ahead? Ebenyi Michael, can you go ahead?
Hello. Yes.
Go ahead.
Yes, I'm talking.
Yes. Yes.
Yes, sir. Yes, sir. Good morning, sir. Yes, sir.
Can you speak?
Toxicants are man-made. Yes. Toxicants are man-made or anthropogenic. Yes.
They're what?
Yes. Yes. Toxicants are man-made or anthropogenic poisonous substance that are introduced into the environment.
That's okay. All right.
Can you hear me, sir?
Very well, very well. Walawa.
Yes, sir.
Can you speak?
Yes, sir. Good morning, Prof. Good morning, class.
Morning.
Yes. Toxicants are either organic or inorganic substances that are harmful to the environment, human body, and the rest, that are harmful to either human body or the environment.
That's okay. That's all right. Jennifer? Jennifer?
Yes, sir. Good morning, sir.
Morning. Can you speak?
Yes, I want to add to what my other friend said. Toxicants can be natural or artificial substances that alter the original state of a thing. It could be water, air, soil, food, the body, plants, animals.
That's okay.
Yes, sir.
So, you see, if I ask everybody to define toxicant, you will define it and you will get something that is a bit different from each of the definitions. But all of them are correct. So that is to say that definitions are never enough. Okay? They're never enough. Somebody wanted to talk. Okay, fine. Let's go ahead. So that is that. I think with that, you have an idea of what toxicants are. But the study of toxicants, okay, as they affect the host or affect the environment is known as toxicology. Okay, so it has a traditional definition, the science of poisons. That is toxicology. Toxicology is the science of poison. I know that poisons are toxicants and agents, as you have said, be it organic, be it inorganic, be it natural, be it synthetic, okay, can cause harm to humans, and not just humans, but other organisms. But toxicology is a study of how natural or man-made poisons, that is toxic substances, and physical agents cause adverse effects in living organisms, right? They are capable of causing harmful or what? Adverse effects. So what is harmful or adverse effect? Okay, these are damaging effects that are damaging either to the survival or normal function of the individual. So when you say something is harmful or it has the potential of causing adverse effects, it means that it can cause damage, okay? Cause damage. If there's anything that can cause damage to your survival or your normal function, then that has harmful effects. Then toxicity describes the degree to which a substance is poisonous. Toxicity has to do with the degree to which a substance is poisonous or can cause injury. There are some chemicals that are not toxic, or their toxicity is small. So if you have a chemical that has low toxicity, then it means the harm that it will cause will also be what? Will be low. But you have substances that are highly toxic, that have what is called high toxicity. So those ones can cause, even death and so on and so forth. So toxicity depends on a variety of factors. One is dose. And I mentioned dosage in our earlier contacts. I said that the dosage is very important. You may be exposed to a particular chemical, but you may not feel any impact because of the dosage. If the dosage is low, okay, the dosage is low, then it means it will cause minimal damage. But if it is high, if you take high dosage, it will definitely lead to, bigger effect. So toxic, to poisonous or deadly effect. So these are just terminologies that I'm just trying to put them across to you. So toxicant, you have said it, is any chemical, be it natural, be it inorganic, be it organic, that can injure or kill humans, animals, or plants. Okay? You have a number of these poisonous chemicals. They could be byproducts, or they could be even the parent material, right? Like dioxin is one chemical that is generated through the burning of tires, burning of some products. There are some that are less toxic compared to their metabolite, like DDT. DDT metabolizes to what is called DDD. And it has been established that DDD is more toxic or harmful than DDT. That is what research has shown, that DDT is less harmful than DDE. DDE, that is just a byproduct or a metabolite of DDT. You have toxic substances like arsenic, mercury, very, very toxic. All right. So you have some of these toxic symptoms, toxic effects. Toxin. A toxin is any poisonous substance or microbial, bacteria, or other tiny plants or animals, vegetable or synthetic chemical origin that reacts with specific cellular components to kill cells, alter growth or development, or kill the organism. So these are, there are a number of terms here that you need to know. Selective toxicity, okay? Selective. Say this person is so selective. Okay, you select your friends. It's not everybody that you are friends with. Okay, the chemical that produce injury to one kind of living matter. And it's very selective that it will not produce to others, only one kind, without harming another form of life. If you are there, you are not harmed by it. It is only the one that it can harm that it will harm. So even when the two live together or coexist together, you will not feel any harm or injury. There is that one in which it is selective to that will be affected. So how does toxicity develop? A substance must come into contact with you, not you per se, but with a body or a surface. It could be your skin, or it could be skin, eye, and so on and so forth, digestive, respiratory tract, at certain dose or the chemical to cause toxicity. So that is the first line of toxicity. It must first have contact. Now, what is dose? What is a dose? The dose is the amount of chemical that enters the body. Okay? The dose received may be due to either acute, that is short term. When you're talking about acute, dose, or acute dosage is short time, or chronic, that is long time. Chronic is long time exposure, but acute is short time exposure. So an acute exposure occurs over a very short period, like we have said. These are self-explanatory notes. These are things that you can read and easily understand, okay? So within 24 hours, very short time, usually 24 hours. The chronic exposure occurs over a long period of time. It can be weeks, months, or even years. So the amount of exposure and the type of toxin will determine the toxic effect. So how much of it has entered your system or has entered the system, and the type of the toxin determines the toxic effect of that chemical. Any question at this point? Or contribution? Hello?
We are with you, Prof.
All right. I'm happy that you're always with me. So what is dose response? Dose response. Mind you, if a particular amount of chemical enters an organism, there is bound to be a response. Is it not so? There's bound to be a reaction towards that. Yeah. And we can measure the response. We can measure this relationship, dose response relationship. It is a relationship, okay, between exposure and health effect that can be established by measuring the response relative to an increased dose. So if you have different dosages of, let me say, a particular agrochemical, you have prepared them maybe in different concentrations. Let's say maybe 5 milligrams per liter, 10 milligrams per liter, 15 milligrams per liter, 20 milligrams per liter, 25 milligrams per liter. These are different dosages, is it not so? And you now administer those dosages to maybe rat or rabbit, and you are measuring maybe how much of diabetes that may induce into that animal or rat or rabbit. So you are varying the dosage and you are measuring the response. Okay, in this case, the effect, which is what? Diabetes. So when you apply or when you ingest the rat or rabbit with 5 milligrams of a particular chemical, how much of the diabetes will be found? That is the response. If you induce with 10, how much will be found? 15, 20. Then you are able to plot a graph, okay? And then you look at the dose response, relationship on that graph, so to speak. So dose response, the relationship between exposure and head effect that can be established by measuring the response relative to an increasing dose. You hear that? You have 5, 10, 20, 25 in that order. And then you are administering and measuring the response. All right? So increasing dose, a dose or a time of exposure to a chemical, drug, or toxic substance will cause an effect, that is a response, on the exposed organism. I think I've explained that. So the higher the dose, the greater the response or the effect. This is the meaning behind the statement, the dose makes the poison. So it is the dose that actually makes the poison, all right? And not the poison, they say. Well, that is just a lighter note. But me, even if it is 0.0001 me, I know that that chemical is poisonous. I will not take it. It's not advisable. Okay? You don't try God. So let us look at more terms as I use here. What is the threshold dose? We have what is called threshold dose. Threshold dose. Threshold is like a limit, okay? Threshold, what is a threshold? It's like limit. So, given the idea of dose response, there should be a dose or exposure level below which the harmful or adverse effect of a substance are not seen in a population. So we're talking about threshold in toxicology. It is the limit at which a particular chemical will be administered, but you will not see any effect. Okay? But if you go beyond that limit, you will begin to see effect. All right? That is what we refer to as threshold dose. That is the level below which you can experience any effect of a substance in a particular population, so to speak. So if, for instance, you administer 1 milligram per liter of poison to a rat and you don't see a response, and you administer 2, you don't see a response, there is a concentration in which if you administer, you will start seeing response. Okay? So that dose at which you applied and you did not see any response is what we are referring to as threshold dose. Okay? You may go up to 3, and then maybe by the time you administer 4, you started seeing response. So in this case, you can see that your dose, your threshold dose is 3, because anything beyond 3, you start seeing a response or you start seeing an effect. So that dose is referred to as a threshold dose. This dose is also referred to as no observable adverse effect level, because at that point, you don't see any effect. So you can refer to it as no observed adverse effect level. Or you can simply say it is the no effect level, NEL, or NOAEL. Do you understand? Hello? Are you with me? Hello?
We are with you. We are with you,
Thank you very much. I'm happy you're with me, but I think we can round up for now and continue by 1 o'clock. All right? Hello? If there
yes,
are
sir.
no
Very well, sir.
So if there are no
Very well,
concerns, we'll resume by 1 p.m. and continue. I'm hoping that by tomorrow we should be very close to the end of the note, so that by Friday we'll have some time together to look at very few concerns that you may have. Also to be jotting them.
Thank you very much, sir. Yes, sir.
Welcome. Okay.
All right,
So
Prof. Thank
see
you.
you 1 o'clock.
Yes, sir. Let's greet Prof.
Thank you very much, sir.
You're welcome.
Thank you, sir. Thank you, sir.
Thank you very much, sir.
Thank you very much, sir.
Thank you very much, sir.
Thank you, sir.
Appreciate, Prof.
Thank you, sir.
We appreciate the strong lecture. Thank you for the
Thank you very much, sir.
You're welcome. You're welcome.
Thank you very much, sir.
Thank you.
We are so grateful
Thank
for the
you.
class, Prof. Indeed, it's a wonderful work.
Very much, Prof.
Thank you very much, sir. We appreciate
It's a wonderful lecture.
Thank you.
Thank you, sir.
Yeah, there are more people posting in the comment section, in the chat box.
We thank God for the high-degree network of Prof lecture today.
12.
All right, thank you very much. Let's call it a day, the evening, and the afternoon.